In this video, we're going to review Chapter 11, starting with the kinetic molecular theory, which consists of 5 assumptions that we make about the behavior of gases. The first is that gases consist of many tiny particles that are very far apart relative to their size. The second is that the collisions that exist between gas particles and between particles in the walls of the container they're enclosed in, they are elastic, meaning that no kinetic energy is lost during these collisions. The third is that gas particles are always in continuous random motion. The fourth is that there are no attractive forces or repulsive forces between gas particles. And the fifth is that the temperature of a gas depends on the kinetic energy of the particles of that gas. Some take-homes here are that gas particles essentially take up no space, which explains why gases have a very low density. And gas particles also experience essentially no intermolecular forces, and that explains why gases expand pretty much infinitely and why their particles move completely randomly. KMT also explains why, at the same temperature, heavy particles will move more slowly and lighter particles will move more quickly, since by definition they have the same kinetic energy on average. The assumptions that KMT makes are not perfect. They fail under conditions like high pressure, in which case the gas particles will actually have a noticeable volume relative to the volume that they occupy, and also KMT fails at low temperatures when particles are moving slowly enough that they can actually feel each other's intermolecular forces as they go by each other. Moving on, we have pressure, which is defined as force over area, and pressure explains why a sharp knife will be able to cut something that a dull knife won't, even if the same force is applied. Pressure has many units. The atmosphere, the kilopascal, and millimeters of mercury, torr, and bar are essentially names for the same thing. So 1 atmosphere is 760 millimeters of mercury, torr, and bar, and also 101.3 kilopascals. Temperature can be measured not only in Celsius, but also Kelvin, which is an absolute temperature, and starts from 0. Kelvin is Celsius plus 273 degrees, and Kelvin must be used in all gas calculations. Next we have STP, or standard temperature and pressure, the temperature being 273 Kelvin and the pressure being 1 atmosphere. On to the gas laws. The combined gas law is used for calculating the changes in conditions of a consistent sample of gas. It is P1 V1 over T1 equals P2 V2 over T2. If we hold temperature constant, then pressure and volume are inversely proportional, and that is Boyle's law. Charles's law states that when pressure is held constant, volume and temperature are directly proportional. And Gay-Lussac's law states that at constant volume, the pressure and the temperature are always going to be directly proportional. Avogadro's law states that the volume a gas occupies is proportional to the amount of gas there is. And Avogadro's law and the combined gas law lead us to what is called the ideal gas law, which is Pivnert. Note that you can use any pressure and volume as long as the gas constant is in the correct units. 3 common gas constants are as follows. The ideal gas law is useful for situations in which conditions are constant. For example, we don't see an initial and final pressure or temperature or volume. An application of the ideal gas law is that at STP, the molar volume is equal to 22.4 liters. That meaning 1 mole of any gas will occupy exactly 22.4 liters if at STP. Another application of the ideal gas law is PIMDIRT, which brings in molar mass and density. You can use this whenever given or asked for the mass, which is a suggestion that density is relevant, or the identity of the gas, the formula, which gives a hint of molar mass being important. Next, we have Dalton's law of partial pressure, which simply states that the total pressure of gases in a system is equal to the sum of the pressures that each individual gas exerts. This becomes useful in gastroichiometry. In situations where gases are collected over water, we need to subtract out vapor pressure that is exerted by the water vapor over the gas, and that will tell us the pressure exerted by the gas being collected. Also in gastroichiometry, remember that if you are at STP, you can simply convert between moles and liters using the molar volume. However, if you're not at STP, you will have to convert between liters and moles using Pivnert. That's all for this video. I hope it's been helpful. Feel free to leave any questions or comments in the comment section below, and thanks for watching.